Let's continue our discussion of 2.1, the tangent and velocity problems, by looking at the velocity problem. What if I told you that I traveled from Moorhead to Lexington, which is about, we'll say 60 miles. I know it's a little bit farther than that, center to center. We'll say it's about 60 miles, and I did it in 45 minutes. What would you say? You'd say I'm probably going too fast. But what if I asked you what my average velocity was in that time? So again, let's suppose that we went from Moorhead to Lexington. So the distance traveled then is 60 miles. And let's suppose that the time we did it in was a rather crisp 45 minutes. And I wanted to find the average velocity. The average velocity that I traveled. Well, what would you do? You would say, all right, well, I'm going to take how far you traveled, which is 60 miles, and divide that by the number of minutes, which is 45 minutes. Now, this is going to be in miles per minute. If I'd like to do it in miles per hour, I need to convert 45 minutes to hours. So I would take 60 divided by 0.75, since 45 minutes is 3/4 of an hour. And when I did that, and took 60 divided by 0.75, I would get a pretty quick 80 miles per hour. That was my average velocity in that trip if I traveled 60 miles in 45 minutes. And so, as our book points out, in general, our average velocity, if we wanted to calculate the average velocity of something that is moving, what we need to do is we need to take the change in position of that item and divide that by the corresponding change in time. Well, if you remember what we were doing in solving the tangent problem, we were doing something very similar to this. We were measuring the change in position and then dividing that by the change in the independent x value. So we're looking at the change in the y values of a function divided by the change in the x value. Well, if we think of our y values as our position and our x values as time, then what we can think of the tangent line problem is looking at average velocity. The secant lines we can think of as average velocities. So I don't know if that makes any sense. Let's look at an example and maybe we can make some sense out of that. Let's take a look at a problem similar to number 6 in your book. Let's suppose that an arrow is shot into the air from the surface of the moon with a velocity of 58 meters per second. And so the height, h of t, is going to be given by 58t minus, we'll say, 0.83t squared. This is a function that tells us the height of an arrow if it's shot up, straight up on the moon with a velocity of 58 meters per second. Now, what we want to do is find the average velocity over the given time intervals. So we want to find the average velocity over the time intervals from t equals 1 second to 2 seconds. Well, what are we going to do? We're going to take the change in position. So we're going to take the change in position divided by the change in time. And what that's going to give us then is the average velocity of the arrow over that time interval. So the change in position, well, that's going to be the height of the arrow after 2 seconds minus the height of the arrow after 1 second, divided by the change in, I said velocity there, we mean time. See if we can get rid of that. Divided by the change in time, so that's going to be just 2 minus 1. Now what is h of 2? Well, h of 2 is 58 times 2 minus 0.83 times 2 squared. That's h of 2. Minus h of 1, which is 58 times 1 minus 0.83 times 1 squared. All that divided by 2 minus 1, I can do that one in my head. That's 1. So let's see what we get here. When we take 58 times 2 and subtract 0.83 times 2 squared, or 4, that gives us, looks like 112.68 minus the quantity of 58 minus 0.83, which is equal to 57.17. Divided by our change in time, which remember we went from 1 second to 2 seconds, so that change in time is 1. And that gives us then a total of 55.51. Now, what's the unit on that? Well, let's see. We were given that the arrow had a velocity of meters per second initially. So the height is given in meters, and the time is given in seconds. So the unit on this is going to be meters per second. The average velocity of that arrow from the first second time t equals 1 second after it's shot, to time t equals 2 seconds after it's shot, is 55.51 meters per second. So what we're asked to do then in the rest of number 6 in part A is look at this average velocity over intervals of time, but those intervals keep getting smaller and smaller. For example, in part 4 of part A, we're asked to find the average velocity of this arrow from the time t equals 1 second to 1.01 seconds. So from 1 to 1.01. Now, notice our interval here is much smaller than what we started with. In the first part, part I of part A of number 6, we had a whole full second interval. Here we have just 1/100th of a second interval. Well, what's our average velocity here going to be? Well, just like we said before, it's going to be the change in the position. Well, the change in the position is going to be the height after 1.01 seconds minus the height after 1 second, all divided by the difference between these two things, this time interval, 1.01 minus 1, which of course is 1/100th of a second. So we have h of 1.01, and so that's going to be 58 times 1.01 minus 0.83 times 1.01 quantity squared minus, well, we put 1 in to the function. We have 58 times 1 minus 0.83 times 1 squared. All of that divided by, again, 0.01, the difference in our time interval. And if you put that into your calculator, what you're going to end up with is, well, let's see, approximately 56.3317 meters per second. So the average velocity from time t equals 1 to t equals 2 was 55.51. The average velocity from time t equals 1 to t equals 1.01 was 56.3317. Now if you do part 5 of part A, I'll just go ahead and give you the answer so you can check and see if you got the right thing. The average velocity from, let's see, part 5 was 1 to 1.001. So we're looking now at 1/1000th of a second. The average velocity over that time interval is approximately 56.33917. So you can see then what's happening here is that this average velocity is sort of locking on to what we're going to call our instantaneous velocity. And that's what we're asked for in part B. In part B, we want the instantaneous velocity at t equals 1 second. And what we've been doing here is we've been really finding slopes of secant lines to this graph. If we were to graph the height of the arrow as a function of time, this is going to be a very crude sketch, but notice that when time t equals 0, that the height is going to be 0. If you look at the formula of the function, what we're going to have roughly is something that looks like this. Okay, so it's going to be a parabola opening down because the t squared term gives us a parabola, and because that t squared term is negative, as you can see from the original function here. Where is it? Right here. T squared term is negative. That means it's going to be opening down. Alright, so let's suppose that maybe t equals 1 is right here. What we've done is maybe t equals 2 is right here. This is a very rough sketch. What we found originally in part I of part A is we found the slope of this secant line, and that slope is the average velocity of the arrow between time t equals 1 and t equals 2. What we did then is we're going to be moving this secant line down, 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 and the last one we did a secant line here from 1 to 1.001, which obviously we can't draw real well here. Well, that's the average velocity over that 1/1000th of a second. And so that's going to be getting closer and closer to the actual velocity of the arrow at that point. What's the actual velocity of the arrow? The actual velocity of the arrow is the slope of the tangent line. The instantaneous velocity, I should say, is the slope of the tangent line. So that's going to be the slope of the tangent line at t equals 1 on our graph. And judging from what we did, because we did the average velocity over in smaller and smaller intervals, as we get closer and closer to 1, we got 56.339. This is the best approximation we have. If you wanted to, you could go from 1 to 1.0001 or 1.00001. You would get farther and farther out in terms of accuracy on the actual instantaneous velocity of the arrow at that time t equals 1. We would say then about 56.34 maybe meters per second is the instantaneous velocity of the arrow at the point t equals 1. And again, that corresponds to the slope of the line tangent to the curve that represents the height of the arrow at time t. So that represents the slope of the line tangent to the curve at t equals 1. So the slope of the line tangent you can think of as the instantaneous velocity, how fast the object or the function is changing at that particular moment in time. And that's what we mean by the instantaneous velocity problem. And so that's about it for section 2.1. You should be in pretty good shape to do your homework once you have the password for 2.1. And the password that you'll need to get into the homework is omphalos, which means a focal point, a central point, point of focus, or a hub. And this problem, the tangent problem and the instantaneous velocity problem, is going to be a focal point or a hub or an omphalos of Calculus 1. Good luck on the homework. Let me know if you have any questions.